Hello friends, today's question. An ideal gas is enclosed in a vertical cylinder container and supports a freely moving piston of mass m. The piston and the cylinder have equal cross-sectional area A. Atmospheric pressure is P0, and when the piston is in equilibrium, the volume of the gas is V0. The piston is now displaced slightly from its equilibrium position. Assuming that the system is completely isolated from its surrounding, show that the piston executes SHM and find the frequency of oscillations. So in this case, we are given that there is a cylinder and it is having, suppose this is a piston, and it is said that this piston is free to move, which is having a mass m and cross-sectional area is A. Atmospheric pressure is given as P0, and this is, let us suppose, initial condition. And then in the second part, this piston is slightly displaced from its position of equilibrium. So this is the position of the equilibrium, and let us suppose it is slightly displaced in this direction, and this displacement is given as small x, slight displacement. And we have to prove that an important part is that this system is completely isolated from the surrounding. So basically the entire process of the compression which is taking place, we assume that is pushed downward direction. It is not mentioned in the question, or it can be pulled upward also. So we can say it is displaced slightly from its equilibrium position by a displacement of x. And for the sake of convenience, let us say that it is moved in the upward direction by a displacement of x. Okay. So this is your final condition. So initially it is given that the piston is in equilibrium. Okay. So let us start from the equilibrium condition. Equilibrium condition. So it means under equilibrium condition, the pressure exerted by the gas inside the cylinder is supporting the piston, okay, because the piston is not moving. You can say in equilibrium condition, the pressure exerted by the gas inside the cylinder supports the piston. Supports the piston. Okay. So which basically means that the forces which are acting on the piston will be in equilibrium. You can say that forces acting on the piston are in equilibrium. So it means the downward force that will be acting on the piston will be equal to the upward force that will be acting on the piston. So in the downward direction, there will be two forces. One force will be because of the pressure, atmospheric pressure, that is P0, and another force will be in the downward direction, will be because of weight mg. Okay, and the upward force will be because of the pressure that is being exerted by the gas which is inside the piston. So in the upward direction, there will be pressure exerted by the gas, force exerted by the gas because of the pressure, and we say let that pressure is given as P. So P is the pressure because of the gas, P naught is the atmospheric pressure, M is the mass. So this P multiplied by A will be balanced by P naught plus P naught multiplied by A plus mg. So we can write it here that upward force due to gas pressure will be equal to downward force due to weight of piston and atmospheric pressure. So we say downward force will be equal to P multiplied by A, that will be equal to mg plus P naught multiplied by A, where P is the pressure of the gas inside the container, P is pressure of the gas inside the container, and P naught is the atmospheric pressure A is the area of cross section for the piston. A is area of cross section of the piston, and M is given as mass of the piston. M is mass of piston. So we can remodify, or we can say we can write this equation as P, that is pressure inside because of the gas, can be written as P naught plus mg upon A. This is one of the equations which we are going to use later on. So we can say this is the equilibrium pressure inside the gas. We can write this is the equilibrium pressure inside the gas, inside the cylinder, that is P, and we can write same formula, P naught plus mg upon A. Now let us consider the second case, that is the displacement. Displacement of piston. So we say that the piston is displaced by a small displacement x from its equilibrium position. We say that the piston is displaced from its equilibrium position by x. Therefore, the new volume in the gas. So now we assume that the piston which was having this as its initial position is moved up little bit by distance x. So this is our movement of the piston towards the outward direction. So therefore we can write that new volume in the gas volume of the gas, if it is given as V, then this V will be equal to old volume plus the volume which, because of the displacement x, that is area multiplied by x. And it is given that the entire system is isolated. So it means it is a adiabatic process. You can say as the system is isolated, that is, we have a adiabatic process, and in this adiabatic process we know the product of pressure, volume raised to power the coefficient, that is adiabatic index, is nothing but constant, where this gamma is our adiabatic index. And it is given as the ratio of Cp upon Cv, which is no doubt we are not going to, which is not required rather. So we are going to discuss this particular equation under two parts. First will be in the equilibrium condition, and second will be when the piston is displaced. So we can say at equilibrium, condition, which is nothing but initial condition, we can write that our P V naught gamma is equal to constant, and after the displacement, the new pressure, let us suppose, is P prime. After the displacement, the new pressure is P prime. We have assumed it that new pressure is P prime. So therefore we can write, and volume we already calculated, is given by V naught plus A into X. So we can write this as P prime, and this is V naught AX raised to power gamma is equal to constant. So we can combine these two equations, or rather we can write this will be equal to P V naught gamma is equal to P prime V naught plus AX raised to power gamma. And we can solve this equation, that is considered separately, that is V naught plus AX raised to power gamma. It can be written as, or we can say approximated as, V naught gamma, and this becomes 1 plus A upon A multiplied by X, and this is our V naught, and we can write this will be equal to our multiplied by gamma, okay, for small displacement. So this can be approximated. So this is our for small displacement. So we substitute this value in the given equation. We can write this as that P V naught gamma is equal to P prime V naught gamma, and we can write this 1 plus gamma AX upon V naught. This term cancel out from here, and we can rewrite this equation as that P prime is equal to P divided by 1 plus gamma AX upon V naught, which can be written as P 1 plus gamma AX upon V naught raised to power minus 1, and this can be also written as P prime is equal to P 1 minus gamma AX upon V naught. We open the bracket, you can write this as P minus gamma PAX upon V naught. So we are able to find out what will be our final pressure in terms of the given parameters. Now we are going to consider what are the forces acting, what will be the net force acting on the piston. So we can say forces acting on the piston. So therefore, the net force that will be acting on the piston will be because of the difference in the pressure. So you can say net force acting on the piston, let us suppose that is given as F net, which will be equal to P prime minus P multiplied by A. And we already know what is P prime in terms of P. So we substitute it here, we get this as that F net will be equal to, this is our P minus gamma PAX upon V naught minus P multiplied by A. P and P cancels out, so we can write this as minus gamma P A square X upon V naught. So this is the net force that will be acting on the piston. And we also know the relationship between P and, which we calculated, this one, P is equal to P naught plus mg upon A. So we are going to use this relationship and substitute here. So you can say, but P is equal to P naught plus mg upon A. So we can write that F net is equal to minus gamma A square X upon V naught. This is equal to P naught mg upon A. So next we are going to write the equation for the motion in terms of SHM. Next is our equation of motion and SHM. Equation of motion and SHM. So we can write the equation for the motion for the piston, which moved rather for with the displacement x. You can write the equation of motion for piston, that will be equal to F net is the net force acting on it, and this is equal to mass into acceleration. So we get this as mass and double derivative of the displacement. So we have, this is also a net force, this is also net force, so we can equate them and we can write that Fx double derivative is equal to minus gamma A square x upon V naught, and this is P naught mg upon A. And this is nothing but equation for the SHM. So we can write this is the equation for SHM, and which is given as m displacement double derivative is equal to minus kx. Okay, let me write this x here. So we can make 1:1 comparison, and from here we can write that the effective spring constant which is k will be equal to gamma A square V naught P naught plus mg upon A. This is our effective spring constant. Now it is almost done. We can write that the frequency of oscillation we first start with our angular frequency. That is omega is equal to square root of k divided by m, where k is the spring constant. So therefore we can write that our omega is equal to, we substitute value of k, and we get this as 1 upon m, and we have here gamma A square upon V naught, and we get this as P naught plus mg upon A, and this square root. So therefore the frequency of oscillation, that is f, frequency of oscillation f will be equal to omega upon 2 pi, so which gives us 1 upon 2 pi square root of 1 upon m multiplied by gamma A square V naught P naught mg upon A. This is the equation for the frequency of oscillation, which we were supposed to find out. This is equation of frequency of oscillations. So this completes the question. Thank you.